start with a brief moment of mindfulness today. Just to, if that's something you all want to do, and it's definitely something some of you want to do because you told me, and I forget, just gentle reminders. Just gently nudge me. Just have me. Is somebody sitting here? If you mind, I'll just move it real quick, just for the mindfulness things. Let's sit here, pop it right back in there. You got a lot of stuff. Hi. Hey. All right. So, just sitting up straight, shoulders down and back. And your head rising up gently. Imagining a little string attached to your head with a balloon on it. Tuning into the room, some sounds in here. And noticing your body, and your mind's going to go someplace in your body. Just observe where that is, without judgment, let it happen. See if from that location you can expand that awareness of your body all the way down to your feet. Keeping that entire section in mind, in your focus. And extending the awareness all the way up. Maybe you even want to imagine just you're filling up with some warm energy. It's just rising up through your body. Till it reaches your shoulders. Maybe they soften as it passes through. Up through your throat, into your neck. And as it passes through your face, filling your face with warmth from the bottom up, it softens things. So if you're noticing a tension in your jaw, if you're clenching your teeth, if your jaw is tight, as the warmth comes up through that, you feel a softness manifest, just a small bit. Up through your eyes, noticing what it feels like where your eyes are. Can you feel the back of your head? Then rising up to the top of your head, can you feel the top of your head? Do you feel any sort of tingling or energy right at the tip, top? Then just letting go of all that visualization and coming back to letting your mind do what it wants to do. watch that transition from focus to freedom. All right, thank you very much, my friends. Okay, I got my glasses. Okay, I almost forgot what was happening. That was kind of a little somnorific. I think I almost put Christian to sleep there. That's a cool shirt, Eric.
Santa Fe.
Yeah, Santa Fe's a cool place. Santa Fe's a rich ass place. But I love being there. But it's expensive to buy lots of big fancy rocks. For lots of money, yes. Lots of turquoise stuff. So, I kind of want to finish up the derivative section this week. And I'm a little torn on what to do today, but I think what we're going to do today is pull together everything that's happened so far. So thinking about derivatives, the applications that we've looked at, and just pulling those ideas together. And I was thinking, I wish I had just started doing this a little earlier. Every time we finished a unit, just kind of pulling things together. But like, I'm doing this a different way. Sometimes I get thrown off. But let's get into that and just warm some things up. Now we might, because of my energy level, not run a full 75 minutes today. Everybody cool with that? I thought it was important that we get together. I didn't want to do another video lecture for y'all. Did everyone find the video lecture? Almost everyone, but now they have. Okay, cool. Please watch that. I'm going to review some of it today, but let's just cap off. And then on Friday, we're going to cover our last application of derivatives, and that's going to be a thing called Lagrange multipliers, which is just a really cool geometric observation turned into an amazing technique for finding maxes and mins in a constrained scenario. So the stuff that I did on, what was that one Monday, was find the min or the max of the function f of x with no constraints. F of xy. Find the xy that maybe make this the least or the most, or maybe something weird in between, like maybe I can't find that, maybe there's a saddle point. On Friday, we will talk about this subject to, and we'll have a constraint in the plane. So we'll have some weird surface, and then in the plane, down here underneath it, we're gonna find the max and the min subject to living only on that curve down there. So this is the curve g of xy equals c, kind of a level curve. And then this is the f of xy up here. And you can imagine that this, if you kind of trace this up here, right, this would have some sort of weird curve image up there. So what's the max and the min? Just restricted to that. It's amazingly simple given an observation that we'll make. But that's Friday. Let's, before we even get to this, let's just do a quick review of some things. And so if I give you a function f of x, y, what is, and I want you to just try to answer this stuff without your notes, just to see where you're at. No karma here, zero penalty. What is that? And what is it? How do you read it? You're probably reading it right now. What does it represent? And then also, what does its magnitude represent? take a minute and really deeply try to answer this question. How would you explain it to someone? Practicing these words and these stories in your mind. Okay. Someone care to tell me something? I'll take anything. There's a number of things a person can say. Brandon, you look like a person who was about to say something.
I was going to say something for the magnitude, but.
Okay, cool. Can you tell me this? Okay, sure.
It's the direction of the largest growth.
That is this.
Oh. Well.
So you're on to something. So this equals the direction of greatest increase. Cool. So if I've got a function, some weird surface up here, and I'm down here at the point x naught, y naught, the corresponding point up here. The gradient tells me what direction down here I should change the xy coordinates so that I move up the steepest upward movement. It points up the steepest slope that I can find. What does this represent? That is good. That is good, man. That's some lawyer-esque shit there. But it sure is true, Czar. It's the magnitude of the direction of the greatest increase. And I think you maybe even said it at the end. What was the last word you said? It was just a stream of consciousness. It's gone now, huh? You got something for me, Corey?
Would it be the amount of increase?
Yeah, it's the rate of increase. It's literally the steepness of that increase. So this tells me the direction in the xy plane to look. This tells me the slope in that direction. So this equals the magnitude of the slope in the direction of the gradient at that point only. Think slope, direction of greatest increase. Slope of its steepness, greatest steepness that I can achieve. Very good. So there was one thing that I hadn't really mentioned before, and I guess because I forgot, but it's pretty cool. How many people have heard the term machine learning? We all heard that term? Yes, yes. So the gradient plays an important role in machine learning. Now, in machine learning, you've got hundreds, if not thousands, to tens of thousands of variables. So your function is some sort of measure of how close you are to the truth. And you've got, maybe 10,000 variables or something insane in there. And so you can imagine this is a 10,000 variable function up here. But there's still only one output. This is your weight function. What we want to do is minimize this in machine learning. So often you want to minimize this because this represents your error in whatever you're approximating. You've got like a truth signal, because when you train an AI, when you train a machine, you've got a truth signal, and then you give it test signals. And you're saying these are all supposed to be this. When you're training it, when you're setting it up, creating the neural network. And so during the training process, it wants to minimize this weight function, which represents the distance you are from the truth. We want that to be low. So you start off at some training condition. You at first feed some loose data into the machine that's supposed to represent the truth. And the first thing they do, or at least one of the common methods, is the method of gradient descent. And you literally follow the negative of the gradient. So it's because if this is the direction of greatest increase, remember that this is the direction of greatest decrease. Steepest decrease. So what you do is you find the gradient at this point, look at the direction it tells you to move, move for just a short bit in that direction, just follow the gradient for a tiny step. Come to a new place, recompute the gradient at that point. And because you might have, these surfaces are very complicated and it might send you down, but you just keep taking small steps in the direction of the gradient, and eventually you get to an approximately minimal value for this thing. Yes, sir?
When you talk about these steps, are they usually by changes of like 1 or even smaller? Or is it just?
Probably smaller. Yeah. Yeah, 'cause these are changes in the, where you say something.
Is that negative?
Thank you. Yes, sir. Yes, it is. Yeah, and so you're just moving down here in the input plane by small amounts. And the smaller that amount, the more accurate your solution will be. But it also takes longer. But so this gradient stuff, like this is a key to machine learning. Yes, sir?
This is sort of unrelated, but if there's like a minima and you get like stuck in a minima and you think it's like the optimal solution, but it's not.
Then you need some kind of potentially other ways to maybe do some random tweaks of it and check some other locations and see if you end up in the same place. That's a great question, yeah. You could end up in a false well, right? So you've got something like this, and there's kind of a little well right there, but just right over the corner, there's this big steep slope that goes down to another well down here. You could get stuck here accidentally. So I think there's randomization methods to just tweak and make sure that you're there. Yeah. Cool, just something I wanted to mention, with certainly not on the skill checks. Which I was kind of thinking, does Monday sound okay for those? Skill checks for the derivative stuff on Monday? Okay, cool. So, okay, blah, blah, blah. Okay, we got all this stuff here. So the gradient, that's a cool use of the gradient. This didn't seem to get any better while I was sick. This rag has never been washed. I'm not sure ever. Wow. So some uses for the gradient. First one is that, so let's go back to the gradient. What actually is the definition of it? How do I compute it?
Be the partial in terms of x, f of x, or f sub 0, y sub 0,
Yeah.
and then the partial in terms of y at that same point.
Yeah, exactly. And if I had more variables, I would just do those different partials along the way. So one component in the vector of the gradient for each variable, that's an input variable. Cool, yeah, thank you. Exactly. So let me ask you some other questions here. If I want to, so we got a weird surface. I can imagine that guy's kind of floating up here a little further out than it looks. If I've got some point, x naught, y naught, down here, and this is z equals f of x, y. And we know now that the gradient direction is going to point in the steepest direction. That kind of looks like that, right? So we'll say that that's, well, the gradient is actually down here, because it's a two-dimensional thing. And it looks like kind of steep that way. So here's the gradient at x naught, y naught. I can imagine that on the surface, but it's actually a 2D thing. lives down there, yes, Dan?
What does the gradient look like when you're at a maximum?
That's a good point. Well, we will get to that.
Okay.
Absolutely, thank you, because I don't think I pointed that out. It has to do with optimization. But if you think about it, I'll just get to your question right now. So let's say that that's the peak right there. So the gradient represents change in the x direction, change in the y direction, local change. You can see that maybe in the x and y direction I have these two horizontal lines right there at a max or a min. Kind of like in calc, right? When you're at a min, wow, that was really bad, but you've got a horizontal zero slope line. So up here you would have partial with respect to x, or equal to 0, and partial with respect to y equal to 0 at that location. So the gradient is the 0 vector.
Okay.
At that point. Yeah, it's a great question. And so what the gradient's telling you, think about that. If I'm at a maximum, and I'm down here in the plane, and I've got a maximum at x naught, y naught, drawings are becoming worse and worse as we move on. But the gradient tells you the direction of the greatest increase. I can't increase here. Does that make sense?
Yeah.
Yeah. So it would be 0, 0. And theoretically, there's no greatest decrease there at the same point. It's kind of all just like roughly flat. So there's no super steep thing nearby. Does that make sense?
Yeah.
Okay, cool. So the gradient's telling me the rate of change in the steepest direction, and here's like the tangent vector that represents that. And the length of that tangent vector is the magnitude of the gradient. The slope of that vector. So this has the steepness equals the magnitude of the gradient. How do I find the rate of change in a different direction? Because I know the rate of change in the direction of the gradient, it's that number right there. How do I find the direction, the slope in this direction, or that direction, or that direction? What do we call that?
Can you multiply it by a unit vector of that direction?
I think that is right. Yes, sir. That's it. We take the directional derivative. So to find, good job, thank you, Emma. To find the rate of change in direction u equals u1, u2, find the directional derivative in the direction of u of f at the point you're interested in doing that at. And that is computed by taking the gradient and dotting it with your unit vector. So keep in mind, this is a unit vector. It has to be. Otherwise, it's going to contribute value to this output. And we don't want this to contribute any magnitude at all. So that's the dot product right there. Now, another thing we know, because I want to think about this for a second in a way that maybe we haven't yet. We also know that this, if I have u dot v, that's equal to magnitude of u, magnitude of v, and that's not necessarily a unit vector there, cosine of the theta, which represents the angle between them. And so this is the dot product, so it's equal to the magnitude of the gradient times the magnitude of u. What's the magnitude of u? 1. Times the cosine of the theta between them. Remember here that that's a unit vector, so it doesn't show up here. So this is a really interesting relationship. Because cosine of theta looks like this. There's 2 pi, there's pi over 2, and right, pi over 2. So this directional derivative, what is the directional derivative when I move perpendicular or orthogonal to the gradient? What is the degree? What is theta? 90. What is cosine of 90?
0.
0. So the gradient kind of ebbs and flows like this. At this point here, think about this quantity. And look at this graph. If I graph magnitude of the gradient, I never thought of doing this before, but I'm going to do it, times the cosine of theta, and this is theta on this axis. The most it is when I'm facing 0 degrees from the gradient. So this right here represents, I'm moving in the gradient, and the magnitude of that thing is the magnitude of the gradient right there. And then as I start to turn away from the gradient, that steepness decreases until I'm facing perpendicular the gradient. So if this is the gradient, right now, that's my fastest increase. That's where I'm going to go steepest. As I start to move this way, that steepness in that curve above me, the tangent slope is decreasing. And right now, it's actually perfectly horizontal. I am not moving up or down if I move in that direction for a short bit. Like it's eventually going to change probably. And then what happens as that theta starts to move backwards? What happens between 90 degrees and 180 degrees?
Start going back up.
What's the cosine doing between 90 and 180? It's not back up.
Right down.
Full magnitude, 0. What's happening? What's the output value? It doesn't go back up. Because I can look at that graph there, right? What is it doing? What's cosine doing?
It's going negative.
It's going negative. So here, full positive. This equals, the rate of change is the magnitude of the gradient. That slowly decreases. It's still positive. As soon as these are 90 and I'm looking in this direction, if I move that way, I don't go up or down. When I start to move here, now I'm actually decreasing until I get to 180 degrees, pi radians, and then that's straight behind the gradient. And I'm moving down at that same rate the gradient is moving up in front of me. That's the least it could be. So this magnitude right here at 180 degrees, this point right here represents the negative gradient. And then as I rotate around a little more, now it starts to become positive, positive, positive. Now I'm at 270 degrees. What's my derivative? Here's gradient. I'm looking 200. Just imagine my hand is 270 degrees from this hand. What is the derivative in that direction?
0.
0. There's 270. The derivative is 0. And then as I come back around, now it starts to become positive. As I start to look in the direction of the derivative again, this all feels really good, by the way, so that's why I'm doing it. And then I'm back up to that full steepness. You see how that works? So, direction of gradient right here. As I turn 90, it comes to 0. As I turn this way, it goes to the exact opposite of the gradient. As I turn this way, I'm back up to 0. As I turn back here, I reach the gradient again. So that's the directional derivative. And you can compute that a couple of ways. You can say, I want the directional derivative in direction u and do this, or you might get a question like this. And I added some web works. Geez, I'm getting out of breath. Man, COVID's a bitch. Sorry, I like an idiot, I took the stairs too. But I didn't want to trap a bunch of people with my potentially COVID-y breath in an elevator. And I've got a reputation to uphold more than anything, the stare guy. So, what if I said, what is the derivative of, what is the derivative of, what is the directional derivative of z equals f of x, y if I look 45 degrees counterclockwise or clockwise from this direction? How can I find that? So this is 0 degrees, that's gradient direction, that's 0 degrees. And I'm saying clockwise. So I'm saying 45 degrees. What's my rate of change? How would I find that? Somebody can tell us in a minute. And I can drink some tea, catch my breath. And this shit makes you feel old. Well, I am old, so I guess there's that too. Anybody got something for me? How do we do it? So let's say here, I'll give you this. Magnitude of the gradient in the gradient direction is equal to 2. No, how about we say square root of 2? For some good reasons. You see what it is, Kayla? How'd you do it?
It's not a blanket.
Oh, sorry, sorry.
If you take the cosine of 45, which is root 2 over 2, and if you multiply that by root 2, which is the magnitude of the gradient, it would just be 1 unit.
Exactly. So, so 45 degrees clockwise from the gradient direction at, I'm being sloppy here, at the point I'm interested in. The directional derivative in that direction, 45 degrees clockwise, that's bad notation, but hopefully it kind of makes some sense. At that point is the magnitude of the gradient at that point, which I gave you, times the cosine of 45 degrees. You just take the cosine of the direction you're looking and multiply it by the gradient magnitude. And so that's going to be square root of 2 times, as Christian said, root 2 over 2, and you get 1 when you do that. Let me ask you this. What is the gradient direction in 225 degrees away from the gradient? So here's gradient. Now I'm moving a whole freaking, you can think of this 2 ways. What's the difference in degrees between these 2 measures? It's 180. What happens to the gradient? What happens to that derivative as you move 180 degrees? Flip, it's pointed down. So this one here is going to be -1. It's going to be literally the opposite of that. Yep. Yeah. So, hopefully that feels a little like, thank God we're talking about this again. Hopefully that's what I'm hoping you're feeling. Like, we should, this is a good thing. We should have been talking about this. All right. So, let's see. I wanted to talk about that. Let's talk about optimization in the last bit of time. These were some things I was just thinking about. I was watching way too many movies and shit on TV. I was telling Christian, I watched The Social Network. Have you ever seen that?
On what?
on Netflix. It's a movie about Zuckerberg.
Oh,
I've heard of it.
Yeah. Oh.
I always forget the name of it.
Yeah. Woo!
Is that a good movie?
It's a great movie, but he's a terrible human.
Jesse Eisenberg.
Yeah, pretty bad. Anybody else watch White Lotus? No? That that must be an old person show.
I started watching it, but I didn't like it because it was too like purposely was trying to make you uneasy.
Yeah, absolutely, yeah. But this season, did you watch this season because it was in
No, I
Thailand?
watched 2 episodes.
Oh, okay,
First
well, this
season.
season's in Thailand and have Buddhism in it, so that's actually somewhat interesting. I understand that. You made me feel slightly less old too, by knowing at least you checked it out. All right. So, let's talk about optimization. And actually, luckily Dan, I guess you're gonna do Dan now. You said it was okay.
Yeah.
So, and not like there's another Daniel here to confuse with, right, Daniel? You're not here. But you will remain Daniel. All right, so optimization. We want to find the extrema. That's an R right there, of f of x, y. So we have a function of 2 variables. We want to find either a minimum or a maximum, and there can be different kinds. Let's just review at least the 2D versions. Let's say just back in Calc 1, here's a maxima, here's a minima. Let's actually do that to just make a point. So here's a minimum. They're all together. They are minima. I'll have to ask my Latin folks, but is that right? The is the plural version. These are local minimums because nearby, if I move in either direction, I move up. This is a local maximum. This is not only a local minimum, it is a global minimum. So it is the lowest point of all that I can find. And the optimization we're going to do here is unconstrained optimization. So find this, i.e. find max min f of xy. No constraints. So you might want to just make a note that there are no constraints. This is called unconstrained optimization. Which has its place, but in like reality, you probably will have constraints, right? Reality has constraints, alas. That is the nature of reality. But we'll pretend like it doesn't for math. Makes math real pretty. So let's think about what happens at a peak. And luckily, because like I said, Dan already brought this conversation to us. So at a peak or a trough, the partial with respect to x naught, this partial with respect to x is equal to 0. If you move in either direction, it's just a local maximum, just like in calculus, where you have no change in that direction. And similarly, the partial with respect to y is equal to 0. And that, of course, as I mentioned a little earlier, means that the gradient at that point vanishes to the 0 vector. Partial with respect to x is 0, partial with respect to y is 0. So this is called a necessary condition for a max or min. If there's some direction of increase or decrease at that point, that means you didn't find the lowest or the highest. If you can still move up or still move down, keep looking. So a necessary, these are called first order because it's first derivative stuff. First order necessary condition for extrema is that the gradient extrema at x naught, y naught, is that the gradient there vanishes. And this is the key to the whole thing. Once we make this observation, we can work from here to solve where this might happen. Now, I'm sure wishing I had some better examples than the ones I don't have, so I have to kind of like make up some shit in my head right now, which for better or worse is what I have to do. So hold on a second. Give me a second. Okay, that's good. Yeah, and then, okay, that's good. So find max min of z equals x squared plus y squared minus plus 2x minus y, excuse me, minus 2y and 4x. Wait, let me get this written up here. So let's find the max min of this thing. So this is my f of x, y. One thing to always do is get a picture when you can, right? So get out Desmos, look at this, see, like, am I expecting this, a max, or am I expecting this, a min, so at least you know what's coming up here? Because this doesn't tell you, well, actually we will know in a minute. But it's always good to have that just sanity check on things. So, step one is find f with respect to x in general, and f with respect to y in general. Can we all do that together, please? This one's not super mysterious or anything. I wish I'd written another one down, but that's okay. Yeah, this one's pretty straightforward. Okay? Yeah, cool. Thumbs up. Nice. We feel good on those. And then I'm going to set those equal to 0. So set the partials equal to 0 and solve. Now here it's super easy because when we set these equal to 0, we've got just, really pretty trivial equations to solve. That's such an asshole math thing to say, the word trivial, but I hope we all find these problems, this problem right here, trivial. I hope this is not a problem for us. Here we get x equals -2. Here we get y equals 1. And so I have this potential extrema at the point -2, 1. Now I don't know what it is yet. You might be able to even gather that it's a minimum because of that positive x squared, positive y squared. They're so dominant, right? When x is really big and y is really big, when x is really big and y is really big, these dominate so much. So like when x is 10, well, let's say x is 100, then this is like 10,000 plus, and if y is 100, this is 10,000, and these are piddly. So like these terms dominate, you expect this thing to be, you expect a minimum, because this thing just grows in every direction. But we've got a great test for this. And the test goes like this. I've really overdone the beautiful turquoise. Let's go for dark blue, that looks nice, I'll keep this purpley back pocket. Okay, so after we find the possible extrema, so the solutions here, all solutions, and there's often more than just this one. All solutions are possible extrema, and we have a fancy name for that. We call them critical points. Critical values, or critical points. And I'll probably say both those things from time to time, but same thing. That means it's a place where the gradient dies. Step 3. Use the second derivative test. Just like good old Calc 1. Remember how that worked in Calc 1? First derivative was 0, and then you took, at some place, you put that in the second derivative and it was positive, you had a minimum. If it was negative, you had a maximum. If it was 0, you didn't know. You had to do something else. Same thing here, except things are a little fancier because we have multiple variables. So the part A of this is compute the discriminant. D, big capital D. And the way to memorize this, the best way to memorize this is the one that includes where it comes from. So it's equal to the determinant, and you can put the word det out front if that helps you. That symbol I was indicating is kind of a determinant-y symbol. It's the determinant of the matrix filled with the second partials. Look at how that rolls. So the top row means the first derivative with respect to x, and then the second derivative was xy. And then the bottom row, the first derivative was with respect to y, and then I did x and y. So notice how first derivatives line up on the rows, and then the second derivative variable lines up on the columns. This is a really pretty way to memorize that. So we compute this thing out. These are functions of x, y. So let's think about how that goes. So that determinant is negative this product. So it's xy times fyx plus that times that. Good old AB minus CD thing, or no, AD minus BC. Maybe I said the same thing twice there, I don't even know. So this is going to be some expression in x and y, but there's one cool thing that I want to just harken back to. If the function is really pretty nice, everything you will have will be this nice. You have to try hard not to. These are actually the same value. So we can just pick one of these two, in partial with respect to x then y, or y then x, and they're the same. They work out the same most of the time. That was Clairaut's theorem way back. So this is actually partial with respect to x, y, because that's the same as that, squared, plus this dude. And I think like in the notes from Monday, I wrote this first when I did. So this is an equation in x and y. Your first thing to do is crank that sucker out. Then what you're gonna do is you're gonna plug each of the critical values into this expression and use the following criteria. So here's a little if-then flow for your calculus code. So plug x naught, y naught, a critical value, into d of xy, because that is a function of x and y. if, here we go, if the value is positive, if d at x naught, y naught is greater than 0. Now is the case where I might have a max or a min. Then you have to go into these subcases. Then if, now to decide, once you got this positive discriminant, you've got a little more work to do. If, now you have to check this upper left value here. You have to see if that thing's positive or negative. So if fxx at that point is positive, then this is the equivalent of that positive second derivative, and I've got a minimum. We have a local min at x naught, y naught. Else if this derivative, sorry for this codiness, I think for some of you it's probably quite fine. I hope, just let me know if it is confusing in any way. If that second partial with respect to x is negative at that point that got us into here, we have a local max. At x naught, y naught. Slow down a little. So if d is now positive, we're now in some new realm. So else if, I hope that isn't confusing. D of x naught, y naught is negative. If this thing is negative at a point, you're so stoked because you're done. What that means is that you have a saddle point. We have a saddle point at x naught, y naught. And remember what that is. That is a place where in one direction you go up, and then in the other perpendicular direction you go down. So there's no max or min there, right? Because up this way you move up, but if you move this way you move down. So we have a saddle point, and there's no, that's not an extrema. But it's cool to know. It might be useful, but we're done. Else if it's 0, then we're out of luck. No information, and we need some kind of deeper test. Yes, ma'am, sorry.
What happens if the partials are 0 in that first, instead of being like positive or negative? If they're
I
just
don't
zero?
think they can be.
Okay.
So that's a really good question. So, yeah, that's a good question. I think I think, I'm not gonna say they can't be, but it would be an inconclusive case. So all we're looking for here, anything that's not in this flow is like, I don't know. That's a great question. No, I'm gonna try to find an example of that. No. Really good question. You should take abstract algebra. Any other questions on this? Because that's it. So now let's finish up our example. And then I can go quietly die in my car and drive home. So do me a favor, crank out the discriminant for this problem. This one's chill. Super chill. Keep track of those partials because you know you still want to look back at that fxx value at some point. So I would, even before you start writing d, just crank those up. Why did I do that? I think that was just there. Yeah, right. Good. hit 2, 2, and 0. And crank up D. And here D is constant, so that's a beautiful thing. But I get used to writing it out, and honestly, the way I wrote it was a little, I think it's just prettier to write it like this with that minus in between. I mean, that's just my mathematician's aesthetic sense, that's just prettier. So we get 2 times 2 minus 0 squared, 4, that is greater than 0. The minute that's greater than 0, I have to go check the sign of fxx. And since that is also positive, so discriminant was positive, second partial with respect to x was positive, what do we have?
Local minimum.
Local minimum. Now, to discern if that's a global or a local minimum, we would have to first locate, well, it has to be a global minimum because it's the only minimum we can find. If we had a series of them, we still would have to be really careful because you could have a function that had a little bump, but then just kind of never actually bottomed out, right? So we have here, I have local min, this is the best local min, least of the local mins, but oh man, down to the ocean floor on that side. So it's a risky business to make assumptions about absolute max mins. But we are going to make assumptions about absolute max mins on Friday when we do this technique for constrained optimization. So there is some web work. Please start working on that, just for your own sake. Don't be like my RCC 400. And don't take my advice or do anything. I don't think you're all like that, but maybe you'll be in my RCC 400 next spring, and that'd be awesome. And then I know some of you are planning on it, and I know that you're people who do things, so that's exciting. That'd be a nice change of pace. Some people who give a shit in there.
Is that a source for union RCC?
It is. It's 430M. Yeah, it's koans, neurons, and the space between. And it'll run next spring, but not probably again for a while. And I'm supposed to Christian, can you hit the button?